Welcome to Ask and Learn.
Okay, so the easiest way to do big O problems is to just analyze it by growth rate. So for part A, we have a function f of x is equal to 10. And O of x, which is the function, the big O function that we're checking it against, is equal to, well, O of x. So let's see if this function f of x has a growth rate less than this linear growth rate, which would mean that would imply then that that function is O of x. So this is a constant function, and the growth rate of any constant function is 0. The growth rate of this function is some linear term. Therefore, we can tell just based on that this first part A would then be O of x. Okay, for the second part, part B, we have a function f of x is equal to 3x plus 7. Okay, so one important thing to know with big O is that whenever you have a term, you only have to consider the most significant term. So we can disregard that 7 entirely. And another thing that kind of idealizes big O is that when you have a big O of x, and then you have some k term, some constant term out there, you can again idealize it as just O of x, because we're talking about a growth function here, and we're talking about mainly degrees of growth. You have linear growth, exponential growth, factorial growth. So the nuances of like the degree of that growth don't really matter as much. So therefore, when we just take that into consideration and we put this, can we big O-ify it? This we can just say is going to grow at a linear pace. And we already know this grows at a linear pace. So then by that definition, it is going to be B O of x. Okay, thirdly, we have the function f of x is equal to x squared plus x plus 1. Okay. And like I said, when we're considering big O, then one of the things that we can idealize all functions as is that growth rate is only defined by their most significant term. And for this function f of x, that's going to be O of x, or that's going to be x squared. And we know that the growth rate of an x squared function is going to be it's going to grow the growth rate isn't going to be constant, because like just if you graph it like a quadratic, the growth rate at this point is greater than the growth rate at this point. And that's kind of the consideration that we have to take with big O. And so the growth rate here is going to be some x squared. And in fact, if we just say like this is some x to the k term, then the growth rate is going to be k to the x, where k is greater than 0. And then also, as we've already shown, this growth rate is linear, this O of x. So this is not O of x. Okay, part D is we're given the function f of x equals 5 log x. So one of the problems when we have this log is that we don't really traditionally we don't really have a traditional intuition of the growth rate of a log function. But if you have some kind of calculus knowledge, then you can take the derivative of it. But that's kind of not the important thing here. The important thing is that we have to know that is this growth rate smaller or larger than the growth rate of a linear function. And if we take that into consideration, then we know that a log function has some growth rate that resembles this curve, whereas a linear function has a growth that resembles this curve. And if we just take a growth rate, so one of the things that's important in Big O is that there exists a growth rate somewhere here, and it doesn't matter that at this point the growth rate of the log function is actually greater than the linear, but just asymptomatically or asymptotically, as we approach infinity, the growth rate of this function is less than the growth rate of a linear function. Therefore, we can say this is O of x. Okay, moving on. Part E is f of x is the floor function of x. Only difference between this and just f of x would be equaling x is that this is a discrete function as opposed to a continuous function. So when we graph it, it's not going to be a line. It's just going to be dots. Because 3.1 would map to 3, all the way up to 3.999 would map to 3. Then as soon as it's 4, everything between 4 and 5 would map to 4. And that's just kind of how this function operates. But we can still observe the growth rate of this function, and we don't even have to make inferences, but we can see that as this function grows and as the x value increases, the rate of the output, even though it might not exist for all points, the rate of the output for all the values is going to grow at the same pace as a linear function. So this would be the definition of an O of x function. And lastly is F. And for F, when we look at this problem, f of x is going to be, again, is going to be a discrete function, and f of x in this case is going to be equaling floor of x over 2. And we can use the same kind of principles that we've learned. Floor of x over 2 is the same thing as 1/2 floor x. Oh, sorry, this is a ceiling function. Doesn't really matter, but just for consistency. Okay, so this is a ceiling function, but same thing. When we have a constant kind of factor, take out the constant factor. The ceiling function of x resembles it's pretty much identical, but instead of it's going to be like when 2.001 maps to 2, so it'll be like that. And this function, the growth rate, even though it's not a continuous graph, the growth rate still resembles a linear function. So just kind of main takeaways: linear and below, they are O of x functions, and anything where you can take the derivative and you can see that it might be a quadratic or a polynomial or an exponential or things like that. That's when it's not O of x anymore. Okay.